In section 3.2, I'm going to do some examples of numerical freefall problems. In this example, we have a rock dropped from a bridge that falls 80 meters before hitting the ground. Part A asks, how long does the rock take to fall to the ground? And part B asks, what is the rock's speed when it hits? So we should start the problem off by identifying the given information and the unknown values that we are to calculate. I'll highlight them here and organize them in a table. The initial speed is 0, and we know that because the object is dropped. Dropped objects start with a velocity of 0. The 80 meters is a distance or a displacement. Now, when we're dealing with problems that involve vector quantities, quantities with a direction, we should define which way we want to make positive. And if we make up our positive direction, that would make the displacement a negative number because down would then be negative. So the displacement is negative 80 meters. We automatically know because when the rock is dropped, when it leaves the person's hand, it's then in free fall. So because it is in free fall, we know that the acceleration is negative g, or g downwards. Part A asks how long it takes. So part A is asking us to calculate a time. So to solve the equation for time, we need an equation. And here's our list of UAM, or uniformly accelerated motion equations from last chapter. We get to use them again. And we want to find an equation with our 3 givens and our 1 unknown. And you can see here that it is the first equation. This equation has displacement, which was given, initial velocity, which is given as 0, time, which is what we're looking for, and acceleration. And then we have another time again. So there's our equation. We can eliminate the term with the initial speed in it because it's 0. So we can just cross that out. With what's left over, we can solve for t squared. I did that by multiplying each side by 2 and dividing each side by a. Then to get t by itself, I need to undo t squared, so I can take the square root of both sides, giving us our solution. And now we can insert the values for delta x and a. When we plug all that into the calculator, we get the time, and it takes 4 seconds for the dropped rock to hit the ground. For part B of the problem, now we know what the time is. We know that the time is 4 seconds. So we now have one more bit of information that we can use to solve for the final speed. So now that we have 4 givens and we're asked for the final velocity, well, really we can use any equation except for the first one. This first one does not have a final speed or a final velocity in it. So we could, if we want, use any of the other 4 equations to solve. And I'm going to use the second equation because, hey, it's already solved for VF. It won't require any algebra. So there's our equation. We can again eliminate the term with V initial in it because V initial is 0. And we can insert the values for a and for time. And we get a value for the final velocity of negative 40. But just pay attention to the wording here. This asked for speed. Remember, speeds are always positive because a speed is the magnitude of the object's velocity. Magnitudes always are positive. It just tells the amount. What this negative sign is indicating is that the direction of the velocity is down. Remember, we had identified up as our positive direction, and so when the rock hits the ground, it's obviously moving down, so we should expect that the velocity is negative. But when we're asked for speed, we don't want to report speed as a negative number. We just simply take the absolute value, and the absolute value of negative 40 is 40 meters per second. Time for a new example. The world record for the highest vertical jump is held by Canadian personal trainer Evan Unger at 63.5 inches. With what speed did Evan leave the ground to achieve this feat, and how long was Evan in the air? So we can start off by identifying the given information and the information that we need to calculate. We have to be careful though, because the givens and unknowns for part A and part B are going to be slightly different. They're going to be slightly different because part A looks at the motion from when Evan leaves the ground until he reaches max height. So we only care about this part of the motion from ground to max height, where part B cares about this motion and the motion back to the ground. So whenever there's a different ending and starting point in two parts of the problem, even though it's for the same motion, you need to treat it like separate problems. So the change in position, or delta x, is given as 63.5 inches. But the acceleration that we know, because Evan is in free fall, is given in meters. So we need to make sure that we are in consistent units. That's why I am converting the 63.5 inches into meters. And I did that with a conversion factor where I know that 1 meter is 39.3 inches. That conversion factor is on your equation sheet. We also know that Evan's final speed or final velocity is 0, and we know that because when he's testing his vertical jump, he's testing how high he can go, and that 63.5 inches is his maximum height. At turning points, objects have 0 velocity. And the question asks, what's the initial speed or initial velocity? So again, we need to look at our list of equations, and we need to identify an equation that has the 3 known values or given values and the 1 unknown value. And notice that we are missing time. There's no time given or asked for. So the equation that does not have anything to do with time is this third one. So that's the equation we're going to use to solve the problem. We'll write it down. And we can eliminate VF. We know that VF is 0, so we can eliminate it. And if we subtract a 2a delta x from either side, that gets V initial squared by itself. But we're not solving for V initial squared, we're solving for V initial, so we need to take the square root of both sides. Now that we have our solution, we can insert our values, and we can crunch the numbers, and we end up with an initial velocity or initial speed of 5.69 meters per second. For part B of this problem, we're considering the motion from when Evan's feet leave the ground until they return to the ground. So we can consider Evan's initial and final positions to be the same thing. Therefore, the change in Evan's position is 0. And this happens whenever an object returns to its initial position, where its final and initial positions are the same thing. We also know that the Evan's acceleration is negative g. We know this because it's in free fall. And we know his initial velocity is a positive, because it's initially upwards, 5.69 meters per second. And we found that in part A of this problem. The question asks, how long was Evan in the air? How long is asking for time. So we're looking for an equation with time in it. The equation with time in it, with the 3 known values that we have, is this one right here. And so when we solve this equation for time, we should notice that this is a quadratic equation. We can use this to solve. We can use the quadratic formula to solve this, but as you'll see here, the constant term is 0, and so there's a special way that we can go about solving a quadratic equation when the constant term is 0. And this we can also have a shortcut if this term is 0. You only need the quadratic formula if all 3 terms remain. So if I simplify this equation, I get that. I combine the 1/2 and the -10. And the special step to solve this without the quadratic formula is to divide each term by t. What that does is it cancels the t from that term. It cancels the t squared from that term. And what's left over is linear. We kept 0 over here because 0 divided by t is still 0. So the algebra from here is pretty straightforward. You can add a 5t to either side and then divide by 5 to get t by itself, which shows that Evan was in the air for 1.13 seconds before he returned to the ground. All right, in this last example, we're shown a velocity versus time graph for a ball that's thrown straight into the air. And we're going to interpret the graph to answer these questions. Part A wants to know what's the ball's initial velocity. Well, the initial velocity is just the velocity when the time is 0. When's the time 0? The time is 0 all along this axis, the y-axis. So the initial speed can be found by determining the vertical or the y-intercept of this graph. And we can read that rate from the graph. It's 20 meters per second. Part B wants to know, at what time did the ball reach its maximum height? Well, we have to know that when an object reaches its maximum height, it's at a turning point. And a turning point occurs when an object's velocity becomes 0. So we want to look for where the velocity is 0. Well, this happens where it intersects the horizontal axis, the horizontal intercept. And that happens right then at 2 seconds. Okay, now for part C. Part C wants to know, what is the ball's maximum height above its release point? Well, we need to remember that it reaches its max height where it crosses the horizontal axis at 2 seconds. And so we should also remember that the area of a velocity versus time graph is equal to the object's displacement. So we want to know the displacement from when it was released at 0 seconds until it reached its maximum height at 2 seconds. So we can find that area. That area will be a triangle, and that triangle is going to have a base of 2 seconds, and it will have a height of 20 meters per second. So displacement is the area. We're finding the area of a triangle with base 2 seconds and height 20 meters per second. Crunch the numbers and you get 20 meters. So this object traveled 20 meters before reaching its maximum